Following up directly from where we left, we will put into practice what we just learned in the previous video. Let us start with the first problem. Three cars of masses 4 kg, 10 kg, and 3 kg move on a frictionless horizontal track with speeds of 5 meter per second, 3 meter per second, and 4 meter per second as shown in the figure. Velcro couplers make the cars stick together after colliding. Find the final velocity of the train of 3 cars, and whether the answer depends on the order of collision. That is, will it matter if the 4 kg block hits the 10 kg block first and both finally hit the 3 kg block, or if the 10 kg block hits the 3 kg block first and altogether both hit the 4 kg block. The direction of the individual velocities are provided in the diagram. How do we solve this problem? Well, first thing first, we start by identifying whether the collision is elastic or inelastic. Typically, if the question does not say explicitly whether the collision is elastic or not, we should assume the most general situation, or the situation with least constraint. That is, inelastic case. Why did I say it was least constraint? Because in inelastic collision, you are only constrained by the fact that the total momentum of the system before and after the collision are the same. Whereas elastic collision imposes additional constraint, namely that kinetic energy of the system before and after the collision also have to be the same. Another telltale sign that it is an elastic collision is the fact that the cars stick together after the collision. So keep this in mind. When the object sticks together, that is to say they move together at the same velocity after the collision must be inelastic. We thus establish the fact that the collision in this case is inelastic or non-elastic. This implies that the initial total momentum of the system, denoted as Pi, has to be the same or equal to the final total momentum denoted as Pf. This is true regardless of how many collisions occur in between. Assuming that after the collision all 3 cars are moving at velocity v, the computation thus follows as such. Now a couple of things you should immediately take note of. First, the total momentum is given by the sum of individual momentum. But remember, momentum is a vector quantity. They have magnitude as well as direction. And we have to be careful with the direction. We have to be able to distinguish the car moving to the left from the car moving to the right. Well, this is not the first time we are dealing with vectors, and we have a mathematical tool we can use to distinguish direction, Cartesian coordinate. Though it is not a must, we typically follow the same convention as the axis of the coordinate system. That is, we assume any velocity pointing to the positive x-axis to be positive, and any velocity pointing to the negative x-axis to be negative. This explains the negative sign in front of the 4. So please be careful with the direction of the individual cars. It dictates the sign when summing up the momentum. Similarly, we also have no idea initially whether the 3 cars are moving to the left or right altogether after the collision. Well, we do not need to worry about that. The math will take care of itself. And if the answer turns out to be positive, like in this case, it means that the cars are moving along positive x-axis, that is to the right, after collision. If it happens to be negative, that means the cars are moving to the left altogether. Now, does this answer depend on the order of collision? Well, let's see. Let's assume that the 10 kg cart hits the 4 kg cart first. We can compute the final speed of the combined 14 kg cart given as such. This 14 kg cart finally hits the 3 kg cart moving in the opposite direction, and you end up with the final answer. Next, we assume that the 10 kg cart hits the 3 kg cart moving in the opposite direction first. We can then compute the final speed of the combined 13 kg cart. This 13 kg cart then collides with the 4 kg cart, and well, you end up with the same final answer. And of course, these answers are the same with the one we just computed in the previous slide. So the answer to the second part of the problem is a resounding no. The final answer does not depend on the order of collision. As a matter of fact, this is a general conclusion not just applicable to this particular problem, that when multiple collisions are involved, the final answer does not depend on the order of collision. It actually arises from the associative property of vector addition. It doesn't matter whether you add the first and the second term first, followed by the third, or the second and the third term first, followed by the first. The sum of the momentums is the same. So far so good. If everything is okay, let's move on to the second problem. Two gliders are set in motion on a flat horizontal air track as shown in the figure beside. A spring is attached to the rear end of one glider. The first glider of mass m1 has velocity v1 and the second glider of mass m2 is stationary. Compute the velocity of m1 and m2 after the collision in terms of the initial speed v1 and the mass m1 and m2. Alright, that's the question. Same thing, we start by identifying whether the collision is going to be elastic or not. Similar to the first problem, there is no explicit mention whether it is elastic or inelastic. So our immediate reaction is probably to assume the collision to be inelastic. But hey, we should pay as much attention to the figure as the question, especially when the question also made an explicit reference. A spring is attached to the rear end of one glider. What do you think that spring for? Well, it serves as a bumper when m1 collides with m2. So here we have m1 coming in with initial speed v1i. I add the extra I at the subscript to indicate that this is the initial speed or the speed prior to the collision of m1. When m1 hits m2, the bumper helps conserve mechanical energy of the system by absorbing kinetic energy of m1 and converting it to elastic potential energy as the spring compresses. And finally, when it recoils back, the elastic potential energy is converted back into kinetic energy of m1 and m2. If the spring is fully elastic and no energy lost into the deformation of the spring, we should then expect that the total kinetic energy of m1 and m2 after the collision is the same as initial kinetic energy of m1 before the collision, since m2 does not carry kinetic energy initially. In conclusion, this problem involves elastic collision, which means that both momentum and mechanical energy of the system are conserved. From the conservation of momentum, we have the following. Whereas from the conservation of kinetic energy, we have the following. We are then to solve for v1f and v2f, which are the two unknowns from these two simultaneous equations in terms of m1, m2, and v1i. The answers are given as such. I will not provide detailed steps to get to the answer, but I expect you to fill out these details yourself. Hence, I will pause here and you shall continue only after you have done with the details. Hey, don't cheat! I know you have not worked out the details. Go back and try to fill up the steps. Now, if you have finally done deriving the answers, I would like you guys to think how the system would behave in the following situation. A. When m1 is equal to m2, that is to say both gliders are identical. B. When m1 is more massive than m2. And C. When m1 is less massive than m2. Think about it and let me know of your answer during the face-to-face session.